Okay, good. So, good afternoon, everyone. I'm glad to be here. Thanks to the organizer for giving me the opportunity to show my work here. My name is NicolasCerardi. I'm a final year PhD student in CEA-Saclay. And basically, I will present to you today a possible new science case for Athena. So we'll see if Didier is convinced. If he is, he will add a new bullet point to his slide. So I will show cosmological forecasts with Athena wide field imager. And so my goal is to convince you that Athena will bring something unique to cosmology thanks to the detection of high redshift clusters. All right, so that we all start on the same page. I want to recall that clusters are an interesting cosmological probe. In fact, they are both tracers of the expansion history of the universe and of the growth of structures. And you can see that in the simulations here from Borgan and Guzzo, where the clusters are marked in the yellow circles. And you can see that for two different cosmologies, the population of clusters is very different through time. It evolves differently, and it's not only the number of clusters, but also their repartition and their size. So thanks to that, there are many possible cosmological tests that can be run with clusters. And one of the latest major attempts to do so was the XXL survey. So I quote this one because actually Athena cluster survey could look like this. So this was 50 square degrees with X Newton. We can constrain the standard model, but we can also, with clusters, constrain extensions to the standard model. Two examples. First one is the dark energy equation of states. In this, on the left plot from a Jumdar, you see like the distribution of clusters along redshift. And you see that for different values of W, basically the number of clusters changes a lot, especially at high redshift. And where you have the most cosmological signal, it's between redshift 1 and 2. So if you want to constrain this cosmological model, this is where you want to observe clusters. Second case is if you want to test inflation scenarios for early universe, then you can study primordial non-Gaussianities, and they involve like a non-Gaussian deviation in the number counts, and this non-Gaussian deviation in the right plot the non-Gaussian deviation increase exponentially with the redshift. So once again, if you want to constrain this model, you better access high redshift sources. So then the question is how to go for high redshift. If you go with the SZ surveys, we'll have a very large fraction of the sky. Detection will be redshift independent, but so far it's really restricted to high masses, and high mass clusters are not formed yet at high redshift. So you could go with deep X-ray survey. You will access low mass, as shown in the right plot, the black points from XXL. But it's really hard to go high redshift because the clusters get really faint and really small. So as a result, today the most interesting part of the cluster population for both dark energy and non-Gaussianities is today unknown. So we wish for a magical tool, a magical telescope that has a great sensitivity and a smaller PSF. And of course, you know where I want to go. It's called Athena. So we did this study just before the redefinition of the mission. So we have the old, we work under the assumption of the old technical characteristics, a large mirror of 1.4 square meters and a half energy with 5 axons. Then the question is, which clusters are to be detected by Athena, and what can it bring to cosmology in the context of the 20th century? These are like 2 minutes remaining. No.
You can continue.
Okay. Cluster detection, we take the broad assumption that WFI is 5 times sensitive as XMM. And we take like scaling relations from XXL. And we have a base case survey that is in fact an already imagined survey for Athena, but it was designed for IGN science and not for cluster science. So it's add that to another case, maybe that is more optimal for us, and it's 4 times more shallow, but 4 times wider. And these are the completeness limits in the mass redshift plane. So you see that we will be able to access low mass objects up to redshift 2, and this is exactly what we hoped for. We can compare that to other major survey at other wavelengths. And here are the 50% detection limits, competence limit for Euclid and CMBS4. And each time, Athena will access lower mass than these other facilities. So really, Athena will bring something unique for cluster people. These are the forecasted number counts. So this is the distribution for both surveys of numbers counts in Redshift. So about 10,000 clusters in survey B. It's 2 times the number of survey A. So the effect of the surface beats the effect of the depth. And this means that, and especially at high redshift, we have 300 clusters between 1.5 and 2. And if we can compare that to Erosita, so in the case of Erosita, ERAS 8 all sky, in the very, very high redshift range, it's 1 order of magnitude less. So really, the question here is, what is the cosmological information carried by these 300 new clusters? So to answer this, I run a Fisher analysis with 5 best cosmological parameters, some scaling relation parameters. The scaling relation parameters have some priors, but they are in fact quite loose because it's from XXL HSC. Omega matter and sigma 8 are totally free, but importantly, in the context of the late 2030s, when Athena will be launched, we want to be able to constrain the dark energy coefficient of state and the local primordial coefficients. So it's the parameter W0, WA, and FNL. All right, so these are the constraints. These are the constraints if you want to compare survey A and survey B together. So in the case of dark energy equation of state, but also for non-Gaussianities, you see that survey B has tighter constraints than for survey A. This is quite expected, in fact, because we have simply better statistics in survey B, so it yields the better constraints. Then the real question is, what is the importance of high redshift clusters in this analysis? Okay, what is the role that they play? So to study that, you can do a truncated analysis. Firstly, you only look at the results between redshift 0 and 1, and then you extend with the higher redshift bins, and this is what is done in the left plot here. And you see that when you add the higher redshift clusters, it tilts the ellipse of the constraints. So in fact, it allows you to break somehow the degeneracy between the parameters W0 and WA. And in fact, it's a great improvement because between redshift 1 and 2, it's only 15% of your total sample. So it's really not a lot. You should not expect such an improvement in the constraint. But you see that for WA, you have an improvement in the constraint by a factor about 2.4. So this is really significant, in fact. And Athena it shows that Athena will be able to use the leverage of the redshift for cluster cosmology. Another way to understand the mechanism is to look at independently the high redshift constraints and the low redshift constraints. So here, if you compare the light blue ellipse and the orange ellipse, you see that the light blue, which is the high redshift cosmological constraint, is really not interesting comparatively to the orange alone. But when you combine these 2 redshift fronts together, you're not only combining the cosmological information, you are also combining the information on the scaling relations. And this is the reason of such an improvement, because if you take the high redshift cosmological information with the low redshift scaling relation information, it makes this dark blue ellipse here. And then this really well explains how do you end up with the total combined analysis of the red ellipse. So another way to say it is that the low redshift allows you to fix your scaling relation, and this helps your cosmological sector at high redshift. Athena will be able to do so because it covers a very large range of mass and redshift at the same time. So this is where the magic resides. All right. So a quick word on that. We can also provide constraints on the growth of structures up to quite high redshift, more than 1.5. Also quick on that, discussion on the priors. If we reduce the prior on the scaling relation, so it means that if we give more prior information on the scaling relation, it doesn't improve our constraints. It means that, in fact, Athena will be able to self-calibrate consistently in the cosmological analysis the scaling relations at the same time. So this is also very, very handy for cosmological analysis. A final word for answering the question, what is the impact on our work on the design to cost operation? The group of University of Bonn has led some simulations with a wide field imager, and they have derived some completeness limits. If we compare this to our completeness limits, what we see is that for the optimistic case of 5 arcseconds, the completeness in the simulation allows you to detect lower masses than our completeness. So it means that with the previous design of Athena, we were really conservative. And for the pessimistic case of 10 arcseconds of half energy width, we are more in line with the simulations. So with this, we are a bit confident that our results will be robust to the degradation of the PSF. So we are happy with that. All right. This is all for me. So I hope that now you are convinced that Athena will bring something unique to cosmology, and we really need it. The good point is that it's using an already planned survey, so it's like one stone, two birds. And yeah, this whole work has been published this month in INM. Thank you.
So I'm not Axel, Didier still. I'm not Alex because I made the mistake. So yeah, it's very nice talk. There is another possibly there is another possible issue. The background requirement of a WFI is going to be relaxed to something from 5 to 7 10 to the minus 3 per second or something. I don't remember the units. Is it also it should be a limiting factor at some point? And also the 1 kb area is going to also impact you badly for the fine. Not only the angular resolution, but the combination of the two.
Yeah. So for the area of the mirror, we think that if we have a longer exposure, we can recover most of the information. So for us, I think the most critical point was the angular resolution. For the background, it's right. But well, we had really bold assumption about the background here because we didn't know much. But if there is a more clear, if now we have more information on that, we could test how it affects the work.
And the survey strategy is not defined yet. I mean, so there is still room for optimization.
Yeah.
So it's one of the tasks of the new science study team. So it will be optimized based on the capabilities of the mission, but there is nothing which is graved in stone at the moment.
Mm-hmm. Yeah.
Any other question?
I just was wondering what impact on this science could have the selection of a couple of US probes, like Axis on one side and LEM on the other side. I mean, if they, Axis, I think, is supposed to have something like 1 arcsecond resolution.
Yeah.
And a wide field. So I was wondering whether you had done any study with this.
Between so you mean between WFI and AKIS? Sorry, I'm not sure.
Yes, I mean, yeah, I just was wondering whether Axis could do this kind of science and at what level.
I'm not sure that you have, well, I'm not 100% sure, but I'm not sure that you have the same survey speed of this.
I have no idea too. I mean, yeah, I don't know.
Yeah, I think I mean, like, I think that Athena is really optimal in terms of survey speed for that. But I don't know much about characteristics of a case.
Thank you.